Hello, everyone. Thank you for joining our webinar. The topic for today will be Purified and Protect RO, pre-RO dechlorination with the HOD UV. My name is Isaac Itzik Rosenberg, and I'm the CTO of Atlantium Technologies. At the end of the presentation, we will have a Q&A session that will be moderated by Amichai Felder, our VP for Process and Innovation. Both of us will address your questions. Once you will have a question during the presentation or during the Q&A, please post them and we will try to answer all of them. Today's agenda is going to cover the challenge, dechlorination conventional method, HOD for dechlorination and RO protection. We will share with you some case studies. We will end up with a summary and a Q&A session. We will start with the challenge. Free chlorine or free available chlorine is commonly used in water treatment processes for disinfection. However, it can cause damage to water treatment equipment such as reverse osmosis membrane, RO, EDI, mixed beds resins, and others. Some industries should avoid the free chlorine presence in the water, such as biopharma, food and beverage, and others. So there is a need, following the disinfection process, to take out, decompose, eliminate the free chlorine from the water. And this is the subject of this session. Some fundamental about the free chlorine. The free chlorine is composed from three elements: chlorine, Cl2, hypochlorous acid, HOCl, and hypochlorite ion, OCl-. Their presence in the water, in the green, you can see the Cl2, the chlorine. In red, the hypochlorous acid, HOCl. And blue is the hypochlorite ion. Their presence in the water depends on the pH. For example, at a pH 7, you will find 20% hypochlorite ion and 80% of hypochlorous acid, HOCl. If we will take out some of the ClO-, the hypochlorite ion, then the HOCl will decompose as well for keeping the proportion of 20-80 under the same pH. Dechlorination, conventional solutions. We will start with the granular active carbon, the GAC. The benefits of the GAC: readily available, proven method, easy to integrate. The drawbacks: requires large footprint, requires regeneration, might result in extensive bacterial proliferation on the downstream RO or other pipes or equipment. Very often, we are being asked to provide the chemical equation of the process. So this is the reason why we are sharing with you this slide. So the carbon with the HOCl ends up with CO2 and HCl. The HCl is hydrochloric acid. The HCl in the water actually ends up with Cl-, chloride ion. So, illustrating the process in the facility, we have the pre-treatment and we have the RO. We inject the chlorine, and we are taking out the chlorine by the active carbon. Looking at the oxygen level in the water, it's constant. The chlorine and the GAC does not affect the oxygen level. Looking at the food availability in the water, following the chlorine, the complex organic becoming more accessible organic to microorganisms. This is the reason why there is increase in food availability to the microorganism. And following the GAC, it's being reduced. The reason that it's being reduced, look at the bacterial level. Following the chlorine, it is knocked down because the chlorine disinfection capability, oxidation disinfection capabilities. And in the GAC, because of the microbial being added because of the GAC, then the food is being reduced. However, the microbial load is being increased and affect, in this case, the RO membrane, and by this creating a frequent CIP, increase in DP, reduce the water availability of the RO membrane, meaning less water, more energy, more chemical, and so on and so forth. And bear in mind that from time to time, the GAC need to be backwashed and being steamed for reducing the microbial load in the GAC. So energy and water on the GAC itself. Moving the next solution for the next method for taking out the free chlorine, the SMBS or the SBS. The benefit, it's a cheap material, readily available, proven method. The drawbacks might result in RO oxidation were not dosed correctly. This is important to notice because it is not very well known for the users. Might result in intensive bacterial proliferation on the downstream RO membrane, including sulfate-reducing bacteria. It's a chemical, hazardous material to handle, scaling of the RO membrane, and lifetime. Shelf lifetime of the SBS or SMBS is 4 to 6 months. The chemical equation, this is the formula of the SMBS and the SBS. The reaction with the HOCl ends up with HCl, meaning Cl minus in the water. And the SBS with the HOCl ends up with Cl minus as well. Looking at the facility, we are introducing the chlorine. We are introducing the SBS or the SMBS. Looking at the food, the oxygen, sorry, it's being decreased following the SBS or SMBS being injected to the water. The food availability, as before, it's being increased because of the chlorine, and further increase because of the SBS or SMBS, which is actually can serve as a food source for the microorganism. Regarding the bacterial level, it's being knocked down because of the chlorine effect. However, it will be increased because of the food availability in the water following the SBS. You will find mainly anaerobic microorganism because the oxygen level is being reduced dramatically because of the SBS or SMBS effect. So there is microbial load, you will find microbial load on the RO or downstream equipment. And the same, more CIP, less membrane lifetime, more energy, and so on and so forth. We would like to ask you to take part in our live poll. What are you currently using for dechlorination? Please answer the poll. Okay, and the results are granular active carbon 27%, SBS 27%. I don't have free fluorine in the water, the same 27%, and other 19%. Okay, thank you. Switching to the HOD MPUV, dechlorination and disinfection, and one treatment process. Since we are dealing with UV, actually we are dealing with light, electromagnetic spectrum. So traditionally, UV light is being used for inactivating cells by damaging their DNA and RNA. There are two types of lamps: the low pressure, which is monochromatic and emits light at 254 nanometer, and the medium pressure lamp that emits light at a broad spectrum between 200 and 400 nanometer. The UVC is considered to be between 200 to 300 nanometer. UV light with the correct spectrum and energy can decompose chemical substance, provide eye disinfection at the same time. Why eye disinfection? Because the energy, the UV dose, which is needed to decompose chemicals, in our case, the free fluorine, is much higher than the disinfection level. So you are getting at the same time the decomposing of the free fluorine and high disinfection barrier. How it's being done? Now we are dealing with actually photochemistry. For example, in this case, the OCl minus, we have the y-axis is the bound potential. We are introducing UV photons. When the energy that is delivered to the molecular that is absorbing the light or able to absorb the light is increased beyond the bound potential, then we will break the molecular into its elements. In this case, the Cl and the O. So this is all about photochemistry. You need to have a light at the correct spectrum that will be absorbed by the compound, and while elevating its energy beyond the bound potential, then you will break the molecule. In our case, we have the x-axis is the spectrum, the y-axis is the absorption and transmittance, meaning we are using the same scale for both of them. And you can see here the low pressure spectrum in red, 254 nanometer. And you have the medium pressure spectrum covering the between 200 and 300 and something nanometer. The black lines show you the absorption potential or the absorption of the material itself, the HOCl and the OCl minus. You can see here I peak at around 280 nanometer, meaning there is a great absorption of the light of the OHCl minus in this spectrum. The HOCl absorbs the light at this area, and you can see here that there is not a good fit for using the low pressure lamp for decomposing the free fluorine, and there is a great fit of the medium pressure to decompose the free fluorine. On top of it, the water transparency actually behaves like this, meaning it's open when the wavelengths are being increased. So there is a great fit between the medium pressure and decomposing the free fluorine. And remember, when you are decomposing the OCl minus, the HOCl will be decomposed as well in a specific pH level. For sizing the solution, we need to know the clarity of the water for UV, UVT. We need to know the pH. And by this, we can define the needed power for decompose the free chlorine. So in Atlantium, we have a vast experience of sizing and implementing the UV solution based on some parameters that we will require from the specific prospective clients. And the equation, the UV photons introduced to the OCl minus ends up with Cl minus. This is at a pH of 10. So you can see here the chemical equations with the UV photons ending up with Cl minus. Looking at the facility, we have the chlorine injection, we have the UV light. Looking at the oxygen, the UV light and the chlorine does not affect the oxygen. We're having the food availability increase because of the chlorine. And the bacteria. The bacteria are knocked down because of the chlorine, and the UV effect downstream is providing additional disinfection barrier. Comparing it to the SBS and the GAC, actually, we dramatically decrease the microbial built-up on downstream equipment, such as the RO, on any other equipment in the line. What does it mean? In the RO, in the case of RO, less CAP, less pressure, more time, more water production, and so on and so forth. So we have a great fit between for using the UV for dechlorination. No? No. A second, the trouble, small trouble. Okay, continue. So as we have seen, the three methods, the active carbon, the SBS, and the UV, ends up with chloride ion, Cl minus. I put deliberately the seawater as the background picture. Why? Because the RO membrane actually are being used for water desalination. So they are actually dealing on a constant basis with salt, meaning N plus and Cl minus. And they are very much resistive for the Cl minus. So three methods ends up with the same effect. So the UV dechlorination is very much similar to the effect of the active carbon and SMBS by ending up with chloride ion, and that's about it. Where to implement the UV in the facility? This is just an example, starting with a clarifier, multimedia filter, ultrafiltration, anti-scaling, SBS, or active carbon, microfiltration, pump, RO, and post-treatment. Where shall we use the UV? The UV will be used, can be used before the microfiltration or after the microfiltration, replacing the GAC or the SMBS. The advantage of having the UV system before the microfiltration, it will provide a barrier for the microfiltration as well as the RO. By this, you will have less microfiltration replacement, even though the microfiltration is not so expensive, but the downtime might be very significant to an RO treatment facility. we are in, we have installations since 2010, meaning each one of you that will decide to use the UV for dechlorination for sure will not be the first one. It overcomes the traditional method drawback and protect your membrane for biofouling. We put here deliberately the big N because it's doing two in a one. Real-time simplified process monitoring and control. This is very important for any treatment facility, for sure in the RO membrane when you are trying to avoid any oxidation of the RO membrane. So what we're actually delivering to the water is a UV energy, UV dose, which is a function of the clarity of the water to UV, the flow rate, and the lamp output. We are sizing the UV dose, as you have seen before, according to the UVT, the amount of free chlorine that we would like to take out, and of course, the pH of the water. All of it must be very well monitored. How we are doing it. This is a cross-section of the UV reactor. You can see here the lamp. You can see here the quartz sleeve that protects the lamp. You can see here a sensor that monitor each one of the lamps directly, not via the water, directly. And we have another sensor that monitor the lamp via the water. What we are getting from it, we are getting the exact energy that the lamp is emitting, and we are getting a signal of the clarity of the water to UV, which is a UVT. All of it connected to a flow meter provide us all those parameters. It can be another tool in your treatment process for making sure that you are decomposing the free chlorine as needed, as being sized. We are not telling you to take out what you are using today, like the ORP meter or a free chlorine direct measurement. It is a further tool that reacts very quickly in the speed of light for any variation in the lamp or the water clarity. All of it is connected to our local controller that can be connected to your eye level SCADA with all the needed alarms and so on and so forth. So everything is presented to the user and can be delivered to eye level SCADA. Switching to case studies. We are sharing with you the following case study. The first one is natural gas facility in the USA. The flow rate is 600 GPM or 136 cubic meter per hour. The source water is a surface water, and the goal was to provide high disinfection level and knock down the free chlorine before the RO. This is a picture from the facility. You can see here the UV system in line to the pipe that was installed there. You can see here some elements that providing the power to the lamps. And on the back, you can see the RO membrane. So we are actually very much adjacent to the RO membrane. And the effect is great. Longer membrane lifetime, lower capital and operational cost. Switching to another case study, it's a Teva Pharmaceutical. They are getting municipal water with the free chlorine coming from the municipality. The flow rate is 9 cubic meter per hour. And the challenge over there was replacing SBS. You can see here the installation. The unit can be installed vertically or horizontally based on the specific availability space at the facility. And the effect was the same, meaning the ability of the unit to take out the free chlorine. In their case, the maximum free chlorine is defined as 1.5 ppm, and the need is to reduce the free chlorine to a level of undetectable. In our case, we are considering it below 0.02 ppm. So you can see here the UV unit, you can see here the pipe in, the pipe out, and the electrical components that drive the lamp. So it can fit very tight location in the facility. Another case study, in the USA, NicePack, which are producing wet wipers. The flow rate is 110 GPM or 25 cubic meter per hour. The water source is a city water, and the challenge was to achieve to knock down the free chlorine and provide disinfection at the same time, and of course making sure that the EDI following the RO is still kept in a good, meaning not being affected by the free chlorine. So over here, I'm sharing with you a testimony from the site director. You can see its testimony that the unit was providing a great effect with a good ROI that they could measure comparing to their conventional methods on other lines. At the end of the day, we are installed all over that facility with several of dechlorination UV systems. Okay, it's a kind of a small detour that I'm taking you. Alternative to free chlorine. Please note, we have shared this, the next slide, with you during the RO protection webinar that we were conducted several weeks ago. I would like to bring up the ability, if possible, not to use free chlorine at all. This is a case study of a desalination, big desalination facility, 100,000 cubic meter per day, seawater, where they are not using any free chlorine at the facility. Meaning you can consider, if the free chlorine is being added at your facility and not coming from the municipality, you can consider using a good disinfection barrier as an alternative to the free chlorine and taking out the dechlorination by having just disinfection barrier. And you can see the results that we have achieved with that big seawater desalination facility, decrease in CIP frequency, and so on and so forth. At the end of the day, they got more water by 8%, and 8% increase in productivity is a huge number in seawater desalination facility. Those are the market segments that we are actually we have experience installed, and our dechlorination solution, F&B, desalination facilities, power plants, drinking water, semiconductors, semi-pharma and biopharma. Those are examples. Few words about Atlantium. We have thousands of installations globally, offices spread all over, and so warehouses, service team, and so on and so forth. Some of our tier one customers, each one of them is not a one-time customer. We have a return customer that buying the solutions for their facilities. So in order to summarize the key benefits, we are decomposing the chlorine, prevent oxidation damage to the RO membranes, reduce CIPs, reduce cartridge filter replacement, reduce chemical usage, increase permeate recovery, increase production uptime, and prolong membrane lifetime. So those are the main key benefits that we were selected in order to make this slide as a summary slide. Now let's go to the Q&A session. Thank you for now.
Thank you, Itzik. Thank you, everyone, for your attention here. We had a few questions coming along the presentation. I see that more questions are coming now. With your permission, Itzik, I will take the first question because I had some notes and like a rough calculation here. So the first question was, what is the CapEx and OpEx differences of using UV for free chlorine removal compared to other methods like, as we mentioned, activated carbon or chemical dechlorination. So it's hard to say about comparing, because one needs to take into account, of course, the downtime, the chemical usage, and other parameters here. I can give, and I did a rough estimation here, like a case of 50 cubic meter per hour, surface water. So pH was 7.8. I think it's also representative to drinking water. And we had to reduce the chlorine from 1 ppm to undetectable. So I think here we will use a system that consumes approximately 15 kilowatt, and the capex would be in the areas of 40 K USD, and the OPEX need to take yearly, like for lamp changes and for electricity, approximately 10,000 USD. So these are ballpark numbers. Very hard to do sizing on a theoretical case, but I think it can give a good ballpark numbers. Next question, Itzik, maybe I think you should take it. Are there any byproducts, or is it suitable for drinking water applications?
Okay, thank you. The byproducts, actually, we are promoting our technology prior to RO membrane. So following the RO membrane, there are no any byproduct. In a case that there is no RO membrane following a system, please consult with us and we will do it a case by case. But generally, the solution we are proposing for a pre-RO membrane.
Okay, thank you. We have additional question. I'm currently using sodium bisulfite for dechlorination. I'm using ORP and pH meter as a process control. Will I still need them while switching to UV dechlorination? Itzik?
Yes, yes, and the answer is yes. It is recommended to keep the same monitoring process as you have. For the ORP, you will need to readjust the set points of alarm. In case you were using SMBS, it might be that the ORP level, the safe ORP level, will be changed, and this is something I'm sure the ORP meter provider are asking the user to do from time to time.
Okay, and next question. I think I can relate to two questions at once. So first was, are there any specific water quality parameters or conditions that make UV treatment more suitable for free chlorine removal? And we have additional question in that subject. How large is from Latin America, how large is the pH influence on the required power? So of course we have to take into consideration TOC. TOC is something we take into consideration in sizing. The TOC is a scavenger for energy, but it also consumes chlorine. So kind of hard to say where is the sweet spot here. pH, so pH has significant influence on the sizing. In general, doing dechlorination with UV, it's better to do it with high pH. I mean, it's more energy efficient to do it in pH which is higher than, let's say, 7.4, 5, where we see more of the OCl form. The water source is also important to determine, and UVT. TSS, if you have a high TSS in the water, that will also damage the UV efficiency. So I hope by that I answered two of these questions. Next one, in case the municipality is providing water with monochloramine, this is something that we see quite often. So what in case the municipality is providing water with monochloramine to my facility, can the UV be used for dechlorination of the monochloramine. We haven't discussed it in the presentation, but this is monochloramine destruction using UV. Itzik, you want to address it?
Yes. Okay. Monochloramine coming from the municipality, we see mainly in the USA. Or if someone is using RO for municipal treating municipal wastewater that's coming from the facility. The monochloramine, if it's coming from drinking water, please note that the municipalities are sending about 11 months a year the monochloramine and 1 month switching back to free chlorine. This is something important to know. So the monochloramine requires a higher energy. For decomposing the monochloramine, higher energy is needed. However, the target concentration of the monochloramine destruction can be much higher than undetectable requirement as in the free chlorine. So it can be something up to 0.6 ppm, and many times the residual monochloramine coming into the RO, which are not damaging the RO, can provide a further downstream disinfection on the RO membrane itself. So in those cases, we are asking the prospective customer to ask his membrane provider what is the maximum level that he can expose the membrane for monochloramine. And by having this number, we will size the unit accordingly. So we have experience with decomposing monochloramine, and in our cases, the membrane providers were allowing a level which is higher than nothing.
Okay, thank you. So we have additional question here. For this application, is it recommended to use medium pressure lamps? The answer is, of course, yes. If you like, I suggest to go back to the slide where you are showing the spectrum for medium pressure and low pressure lamps. If not, we can address it in other.
Second. I'm getting there.
Okay, so we see chlorine in different forms, meaning different pH. That the spectrum that you require in order to destroy the chlorine, either it's in acid form or in the high pH form, as it's showed in the polychromatic lamp, meaning the medium pressure. You have it is much more suitable. Actually, the low pressure lamps, I hardly hear of application using low pressure UV for chlorine destruction. Correct me if I'm wrong.
No,
I don't think it's used.
It's not being used because of you can see there is hardly any absorption of the free chlorine of the 254 nanometer. So it's not being used for this.
Okay, additional, I think it's a follow-up question regarding the chloramines. What about chloramines in swimming pools? Do you have such experience? Actually, we do. It's in the circulation line, where the pool, the water in the pool are being recirculated via filter and chlorination. So the UV is located in the return line, and it helps managing the monochloramine and the chlorine levels and the ratio between them in the swimming pools. So sometimes it is required by the German standard as something to put in swimming pools. Sometimes the swimming pool owners are choosing to have it in order to reduce the chloramine. Actually, greatly influence the user experience in the pool, meaning they have less burns in the eyes. Additional questions? Just a minute. What considerations should we keep in mind when selecting and implementing UV systems for this purpose? I'm assuming dechlorination in general. So we talked about the water quality parameters when doing sizing. When doing maintenance, and the maintenance here is very, very low, meaning basically it's a lamp change out every 6 months or more. I would advise operators to have extra lamps on site, some O-rings if needed, but these are the spare parts that are needed on site. Again, the maintenance is very low on this system. Next question, footprint. Our treatment area is rather packed. What is the expected footprint while using UV system? Itzik, you want to address this one?
Yes, okay, it all depends on the sizing. As you've seen in the picture, the units can be installed vertically or horizontally. So usually in all of our installation, not only for the dechlorination, we find that we can fit. I've not seen a site that we couldn't fit our system into it.
Okay, last question I see here. How can system operators ensure optimal performance? I think like in most cases, I mean, when using ORP, and I think Itzik addressed a similar question. So when using a ORP after the UV or using some chlorine meter, so this is I think in most cases people use ORP even though it's not direct measurement. But and again, when the UV will require some maintenance, you would not see breakthrough of chlorine. You would see small change. I mean, the ORP will go a little bit higher, but it won't go to breakthrough. Okay, I think we cover all questions. I think last question here is can we get the slide by email, please? Thank you for the presentation. I also want to join in. Thank you for the presentation, Itzik.
Okay. Okay. Thank you all. This is the end of our webinar. The presentation can be, you can send us an email, and then you can get a link to the presentation. Within a few days, it will be posted in our website. So feel free to download it, share it, and so on and so forth. And of course, we are here. Send us a mail for any further inquiries. Thank you all for joining us for this, in our case, evening, morning, afternoon, whatever. Thank you all.
Thank you very much.